Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Thanks for the introduction, and thanks for the workshop organizers to invite me here. Today I'm going to talk about Outlier Pursuit. This is an algorithm that we come up a couple of years ago, and talk about how this algorithm can be used to solve robust principal component analysis and collaborative filtering. These are two different tasks but are closely related. This is a joint work with Konstantin, and also Yudong. He is a student of Konstantin, and Suje. All of these three are within the University of Texas at Austin. Suje is not a student. Yeah, Suje is a professor at UT Anyway, so this is the outline of today's talk. I start with a very brief explanation of what is PCA, although I don't think that's really necessary. And also I need to emphasize a little bit on why PCA is very sensitive to outliers, so that motivates the task that we want to handle. And in the process, we will also try to distinguish two different types of corruption that can skew the output of PCA. One is corrupt features, and the other one is corrupt points. We will see that in some later slides. After this short introduction, then we will discuss our main intuitive idea and the algorithms. And after that, there will be theoretical results in two setups. The first setup is for full observation, where all samples, regardless whether this is a true sample or this is an outlier, you see every entry, every feature of these samples. The other case is in the case that you have a lot of missing observation. So even if a sample is a true sample, but you do not have the privilege to see every entries, you may only see maybe 30% of the features of these samples. And a very interesting application of this setup is, in fact, collaborative filtering. And finally, I will conclude the talk by basically explain from a high level the framework of doing robustness in high dimensional setup. So principle PCA is arguably one of the most widely used statistic tools, especially in dimensionality reduction. So the idea is you have points, you have a lot of points which lies on or approximately lies on some low dimensional subspace. And they want to recover this low dimensional subspace only by observing these points. So the standard technique is basically doing an SVD. So to think it more carefully, if I organize all the points as a matrix, which means each point, you can list each point as a column of the matrix. You list all the points, you have a large matrix, you do an SVD. You do an SVD, and it only take the largest singular values and the singular vectors corresponding to these top singular values. And that will give you a low rank approximation of this original matrix. And it can be shown that this low rank approximation is in fact the optimal with respect to the Frobenius norm, and that's the story of PCA. But because we just say that the approximation is with respect to the Frobenius norm, and Frobenius norm is basically an L2 type of norm. And we all know that if you want to minimize something with respect to L2 error, it can be very sensitive to outliers. So if I put it in picture, this is the true sample set I'm having. I do a PCA, I'm very happy to get a good solution. Now suppose someone else maliciously puts like two outliers with a huge amount of magnitude. So the magnitude is very large. I do the similar SVD. I do the same SVD procedure as I did before, and this will be the solution that I'm finding. This subspace doesn't really capture any information that I really want to recover. And this shows that standard PCA, the PCA using SVD, can be very sensitive even to a very few number of outliers. So to handle this, in this talk we are going to talk about robust PCA. But there's two types of errors which can make the solution of SVD becoming unusable. The first one is called the corrupt feature. So the idea is for each sample, no matter what, it doesn't really matter whether this is a true sample or an outlier. For each sample, some features can be randomly picked and arbitrarily corrupted. So if I put all the corrupted features as a matrix, what you will see is a sparse matrix. So in this setup, there's no clean samples. All the samples are more or less corrupted. But on the other hand, there's no samples which is completely corrupted. So every samples give you some information, but none of them are very clean. The other setup which we'll be focusing in this talk is called the outlier setup. So there are clean samples which are only subject to some small noise, but there's no gross errors. And there are some outliers. If a sample is an outlier, which means every feature or every entry of these columns you cannot trust. Every feature can be arbitrarily corrupted, and it can be corrupted in an adversary way. So our objective here is, given a matrix or given a bunch of points, most of them are true samples, are clean true samples. Some of them are outliers, which is arbitrarily corrupted. And of course, I do not know which one is a true sample and which one is outlier. I want to do two things together simultaneously. The first task is I want to find the subspace which will approximate all your true samples. And on the same time, I want to identify those outliers. I want to identify those columns that has been arbitrarily corrupted. So what is our idea? Now let's rethink of standard PCA. For PCA, what we are doing is we observe the matrix M. I want to find a low rank matrix L such that L will approximate the M. And the constraint on L is the rank of L must be small. Now, of course, I do not have this clean M. Instead, I have some mixture. I have a bunch of mixed samples. Suppose I only focus on true samples. If I approximate those samples, I should get a low rank matrix. Suppose I only focus on the outliers. So I remove all the true samples, that's only outliers. Now, assuming that there's not many outliers, because if you have 95% of arbitrary corrupted outliers, I don't think there's anything that you can do. So suppose the number of outliers is not large. Now the matrix that only corresponding to the outliers will be a column sparse matrix. Because most of columns, those columns are the true samples, they will put it as 0 if you only look at the outliers. So that means if I can approximate my observation as a summation of two matrices, the first matrix corresponding to the true samples, which should be a low rank one. The second matrix corresponding to the outliers, which should be a column sparse matrix. Then I'm in business. So suppose someone can solve this one, this optimization problem, then the L part will give you the true sample, or gives you this subspace that you're looking at. And the column, all the non-zero columns of this C matrix will tell you which points are the outliers. But unfortunately, this is a combinatorial optimization problem. I don't know how to solve it, just as I don't know how to solve other NP-hard problems. So the standard way here is, of course, since I don't know how to solve a non-convex problem, I just relax it to some convex optimization problem. A very typical, not standard technique here is for low rank matrix, if I want to solve something with respect to the rank constraint, I can always using the trace norm also called the nuclear norm, also called the key-find L1 norm, to use that as a convex surrogate of the rank constraint. Now for the column sparse condition, which basically says that I want the number of non-zero columns to be small, for that I can use a norm called the L1, L2 norm. So that's the summation of the L2 norm of each column. So you take L2 norm of each column and you sum them up. Because of the summation basically you can think of that as a L1 norm. So to pick only a small number of columns, which is not completely zero. And within this column, it doesn't matter whether you want the feature to be zero or non-zero. So that's a norm that is now is quite widely used when you want a matrix to be column sparse. So this will be the formulation. This is the formulation that we propose. It's very intuitive, and it is quite easy to think of. The most difficult part, of course, is trying to show that this convex relaxation really works under certain technical condition. But to answer that question, the first question that we need to answer is, when does this formulation not work? So the first condition that we require is, if a direction, if a subspace is given by the true samples, it must be given by many true samples, not a small number of one. What does that mean? So let's revisit this bunch of samples. Of course, this is a true direction. This is a direction that is generated by true samples because many samples contribute to this direction. Now, if someone claimed that these six samples are also true samples, and this is the second dimension of the true space, then this leads to some ambiguity, because this direction is only contributed by six samples, and it is not clear philosophically whether these six samples should be considered as a minority within the true samples, or you should regard this as six outliers. So to avoid this kind of ambiguity, we need to make sure that all the directions of true samples must be represented by a majority of them. And mathematically, this can be represented using the so-called incoherence property of the row space. So mathematically, this means that if I take the SVD of all the true samples, if I take an SVD of the true samples and looking at the row space here, taking any coordinate axis, the inner product must be small. So that means, otherwise, if the inner product is large, basically means that there are some directions which is solely contributed by maybe 3 samples or 5 samples, and that will lead to the ambiguity problem I just said. So to make it rigorous, basically we want the row space to be incoherent. This is a condition that we impose, and this is the only condition that we need. Besides that, there's no other conditions. Now, to analyze the formulation, we start from the noiseless case, which means all the true samples exactly lies on the subspace. There's no noise. There's only outliers, but there's no noise. So the formulation will become a minimized two regularization term, such that the summation of the two matrices will equals to my observation. And this is the main theorem that we get. Basically says that the fraction of outliers that we can tolerate cannot be larger than some universal constant divided by the rank and by the incoherence parameter, the parameter that measures your incoherence of the V space. So as long as you don't have too many outliers, it should be fine. And a lower bound or an outer bound here would be that for any method, suppose you don't impose any assumptions on the outliers, then any method cannot handle outliers which is larger than 1 divided by rank. Because again, if you don't have any assumptions, I can always put outliers on the same direction to make it look like a new direction. basically create the problem being ambiguous. So, but this is more often like a hand-waving argument. So to prove the theorem, to prove this theorem, the method now is quite standard, I would say. So the idea is I want to show that some point, some solution L and C, some solution and C, which has the property that I want. I have some desired property. I want to show that my solution has this desired property. So I've pinned down one point, one solution, which has this desired property, and show that this solution that I guessed is indeed the optimal of my convex optimization problem. And for the second part, basically all that you need to do is do some convex analysis. But the first part is basically the novel part of this work. Typically, for all the previous work that I'm aware of, when you want to show that some convex optimization problems gives the solution that you want, you already know what is the optimal solution. But in this case, it's different. Our first guess is saying that this optimization problem, our previous optimization problem, gives an optimal solution where L star, the L part, is exactly all the true samples, and the C star is exactly all the outliers. But it turns out that's not the case in practice. So if you run some simulation, you'll find that with 99% of chance, you won't get this two clean separation. And the reason but this doesn't really bother us, because we don't need that. All that we want is the column space of L is the same as all the true samples, because we want to do PCA. And also the column support of the solution of C is equal to all the outliers, because we want to identify that. And these are the two properties we want. So the idea to pin down but there are many such optimal solutions, such good solutions. I'm not sure which one is the optimal solution. So how to pin down this optimal solution? We invented an oracle problem. So on top of the original convex optimization problem I'm solving, I added two additional constraints. Each of them impose the requirement that I want. So the first constraint basically says that the solution has the same column support that I want. The second constraint says the solution will have the same column space. The L part has the same column space as the true samples. Of course, I cannot solve this because I don't really know what is the column support of C star and L star. But this will give you some solution, a fictitious solution where it exists, but I do not know the true value of that. And by definition, the optimal solution to this problem satisfies the two properties that I want. Now all that is left is showing that this optimal solution is also optimal even without these two additional constraints. Then if that's true, then I show that the optimal solution to this problem has the two properties that I want, right? So this is basically the main novelty, and the rest is some technicality. We have already pinned down the candidate solution that we want to show, and by some convex analysis, you know that if you want to show this L hat and C hat an optimal solution, there are some equalities and some inequalities that you want to satisfy. You want to find some dual variable Q, a matrix Q, which satisfy those 5 constraints. 3 of them are equalities and 2 of them are inequalities. And the simplest way would be I've tried to find a Q that satisfies all the equalities, and then showing that the two inequalities are also satisfied. Our first guess is using this UV transpose plus lambda H, but it does not work. There are some gaps that you need to correct, but eventually you can correct this Q, and that will give you some candidates which already satisfy all the equalities. And thereafter, then to showing that the inequalities hold is not that difficult. But if you're interested, you may want to read the papers. So this is some numerical comparisons between the formulation, the proposed formulation, with the other formulation, which was proposed by Chandrasekaran et al. And Candace et al. So in their formulation, they're considering the problem that you are doing robust PCA and feature corruption. So many entries are corrupted, but none of them are corrupted on a single column. The setup here is the outlier case, and the simulation basically shows that our formulation, which is tailored for this setup, really performs better than the other formulation, which is not really for this one. You have a question? No. So another view to understand that is this is a philosophical view. If we think of estimating a mean of a bunch of points, this is equivalent to minimizing the L2 norm of you want to find some x which minimize all the L2 norm of the reconstruction, and it is known that this is very sensitive. To make it less sensitive, you can minimize it with respect to the L1 norm, and that will give you the median of a bunch of points, and people know that median is very robust. So it's the same as in PCA. PCA is minimizing the L2 norm, subject to some rank constraint. So an ideal formulation for robust PCA would be to minimize the L1 reconstruction error, subject to the low rank constraint. Of course, I don't know how to solve it. So our method can be sort of as convex relaxation of this ideal formulation. Now, so far I've talked about, all that I've talked about is in the case that you have 4 observations. So you observe all the samples, every entry of each sample. In the remaining part, I will talk about a case where you have some missing entries, even many missing entries. And the motivating example of think of that is for collaborative filtering, also called the recommendation system. So here is this is a picture that people taken from Amazon.com. This is a book that you read. It's a book of 6 steps to spiritual revival, written by some priest. And these are the books that Amazon thinks, if you are interested in this book, you might be interested in. And it's quite clear that it's not really relevant. And the idea that the reason that the recommendation system of Amazon fails in this task is because there are people maliciously adding ratings so that the result of the recommendation system is skewed. So recommendation system, for those of you who are not familiar with recommendation system use basically users rating. So if you visit a website, you see some products, you've used some products, you like some, you don't like some, you may give the rating of 1 to 5 to the products that you like or you don't like. The recommendation system will collect these ratings and to predict your future preference for a product that you've never seen. I believe you will like it or not. But it is very sensitive. It is very sensitive to when there are some malicious users who inject fake ratings. So I can create, yes?
Can you rate without buying on Amazon? You have to buy the thing to rate on Amazon, or can you just go and rate it?
I think in Amazon there's the recommendation system of the Amazon, they take 2 kinds of information. The first information is of course your purchase. And the other information, so only after purchase you can rate, that's correct. But the other information that they are also collecting is the browsing history. So after you read like the cover of this book, you may want to browse the other one, and they also collect that information. Where are we? Oh, okay. But there are some malicious users who try to change the preference, the prediction of the system so that they can promote their own product And there are many popular algorithms which are very vulnerable to manipulation. So how does this relate to our matrix completion? One method to do recommendation system is via matrix completion. So the idea is there's some underlying true preference matrix. I don't see the whole matrix. I only see some rating, which is like a partial observation of the matrix. And I want to recover from this partial observation your true matrix. Of course, you need some assumptions. Otherwise, this is a ill-defined problem. A common assumption here is your user preference is a low-rank matrix. Reason being, whether I like a product or not like a product is only governed by a small number of factors. So, for example, if you like a laptop or not like a laptop, may only depends on price, performance, portability, maybe brand, and that's probably it. So that means the rank will be 4. So given the low rank, given these low rank assumptions, you can basically recover a low rank matrix given the partial observation, and that's the standard method, or that's one standard method at least. But this doesn't really tackle the problem of you having some malicious users. So the idea is the same. To handle malicious users, we still split the matrix in 2 parts. For the true users, for the goodwill authentic users, their preference should be a low-rank matrix. For the malicious users, I have no knowledge of how they will rate, so I just think them as an arbitrary corrupted columns. So all that I need to do is, given the partial observation of all the ratings, I recover the matrix, I split the matrix into 2 parts. One part corresponding to the low-rank matrix, which is the preference of the authentic users. And the other part, I don't care of the values that you put there, but I want to identify the columns. So which are the malicious users? So this is what I just said, put it in picture. So this is the preference matrix. You randomly sample some of the user prediction or user preference, and these are some malicious users, and your goal is to fill up all the missing ones for these authentic users. And the formulation is almost the same as the previous one. I want to minimize the nuclear norm of the L matrix, and I want to minimize the L1, L2 norm of the C matrix, subject to a constraint that for all the observed entry, because I don't observe all the entry, for all the observed entry, Lij plus Cij must equals to my observation. And this is the main theorem that we get from this method. It basically says that if my sampling density, the fraction of entries that I see, is not too small, and if there are not too many users, too many malicious users, then this method works. So to put it in word, basically, if there are constant fraction of, if my observation is a constant, so I observe 20% of the entries, then I can tolerate a constant fraction of malicious users, maybe 3%. So if I observe maybe 40%, then I can tolerate a little bit more, maybe 5% of malicious users. On the other hand, when the matrix grows, it's likely that the fraction of observations goes to 0. You may not be able to maintain a constant fraction of observation. I mean, the observation rate may go down. But even if your observation rate goes down, you can still handle a growing number of corrupt columns. And this is some simulation results which compares the proposed formulation versus the formulation where you basically believe that there are some sparse errors. And you can see that I think it's quite clear that our method is slightly better than this method. So from a high level, In statistics, especially in high-dimensional statistics, this is a very common method. So basically, I want to find some predictor or estimator so that some loss function is minimized. But in the high-dimensional setup, likely I don't have enough samples. So I have to assume that my predictor has a certain structure. It's maybe a sparse vector or a low-rank matrix. So to impose that, I add some regularizer to impose this structure. This is now a very standard paradigm. So our approach is slightly different in the sense that, in fact, it's not common. It's quite common that you don't get a predictor which has one clean structure. It's likely that what you get, the predictor is a mixture of several different structures, and you want to entangle them. So that means that I want to find an x1 and x2. x1 has certain structure, for example, low rank. x2 has another structure, maybe a sparse matrix, so that the summation of them well explains my observation. And in many cases, this approach will gives you both the robustness to your model, basically your model assumption, and also it can be very flexible. And like in today, we talk about this approach can be used in PCA, and it also can be used in collaborative filtering. So these are some papers. That is related to robust PCA and robust recommendation system that have been co-authored in the recent years. And thanks for all my courses. Thank you.
Questions?
Maybe only live question. So I was thinking, like, when you have your points, so if you kind of sample a subset and then try to draw PCA, and again sample another subset and then try to use PCA, do you think like that method would be?
In fact, this is a very standard method in robust PCA. It's called a RANSAC. The problem here is, suppose I have a constant fraction of outliers. If there's only one outlier, your method will work because by subsampling there will be some subset that does not contain this outlier. But if I have 10% of outliers, so no matter how you random sample, the subset will still contains more or less 10% of outliers. So that one really helps you. Right? And unless you subsample a very small set, but probably that will give you too little information to really reconstruct the subspace, even if the subset contains all true samples. Yes?
How do you automatically choose your lambda and lambda 2?
Well, that's a very good question. We have two different lambda value. In fact, there's one value that you can choose based on theorem. So theoretically, there will be a value. As long as you choose this value, you will have a good performance. But in practice, we found that this performance is not as good as we would expect compared to if you do the cross-validation. So in practice, I would suggest you do cross-validation. Because you can, so suppose you're in the noiseless case, you do the matrix decomposition, you will have the L part and the C part. You can always measure the rank of the L and the column, the number of non-zero column of the C, and to see which one is too large, then you can tune your lambda. So by cross-validation, you will get a better practical performance.
Okay, thanks, Shu.
Thanks.